We present dynamic neural cellular automata, a method that enables synthesizing dynamic texture videos in real time. Textures are everywhere. We perceive them as spatially repetitive patterns. Dynamic textures are textures that change over time and induce a sense of motion. The goal of dynamic texture synthesis is to generate perceptually equivalent samples of an exemplar texture video. We improve the performance of existing dynamic texture synthesis methods by 2 to 4 orders of magnitude, both in terms of speed and the number of parameters. We highly encourage the viewers to visit our online interactive demo at the link shown on the video. Given a target appearance image, in this example bubbles or colorful dots, and a target motion, for instance circular motion or hyperbolic motion, our model can synthesize dynamic texture videos in real time. Moreover, to the best of our knowledge, we are the first ones to enable several real-time interactive video controls. The speed slider allows the users to adjust the speed of the motion in the synthesized video. Moreover, the users can control the direction of the motion using the rotation slider. Additionally, since our model only uses local update rules, we can adjust the resolution of the synthesized video in test time. We also allow the users to interact with the video using a painting brush tool. Lastly, the local coordinate transformation panel allows the users to choose between different kinds of local coordinates to create special effects. Now we will provide the details of our method.
Let's start with cellular automata, the origin of our model. The key components of cellular automata include 4 parts. The first one is grid of cells, where a vector S shows the state of a cell at location ij at time t. The next two are the definition of neighborhood and update rule, in which cells perceive their neighborhoods and update the cell state accordingly. Finally, with a handcrafted starting condition, the system can demonstrate complicated behavior in a self-organizing manner. A well-known instantiation of cellular automata is the Conway's game of life. To model dynamic textures, we propose to use neural cellular automata, NCAA here. The basis of NCAA is the cell state, which is a 2D grid with cells living on it. Here, the 2D grid is of size h times w. Each cell is represented by a c-dimensional real vector, so the shape of the cell state is h times w times c. The top 3 channels are RGB channels of the cell, which can be regarded as pixel colors and used for synthesizing dynamic textures. And all other channels are hidden channels, whose usage is decided by the model itself. Starting from a seed state S0 here, NCAA updates the cell state and the RGB channels can be used for training. In one step of update, each cell first perceives its local neighborhood, which is the spatial gradient here, computed by discrete approximations of those operators. Then, all cells apply the same update rule, which is the function f with parameter theta here. The 2 stages constitute the NCAA evolution over time. We propose novel modifications to these 2 stages to make NCAA more adaptable to modeling dynamic textures. In vanilla NCAA, cells perceive their neighborhood by doing 4 convolutions with fixed kernels to approximate the spatial gradient. However, it only does perception on a single-scale cell state. Such a scheme can lead to inefficient communications between faraway cells and thus fail to synthesize desired global patterns. We modify it by doing the same perception at multiple scales to facilitate long-range cell communications. This results in multi-scale perception. After multi-scale perception, there is the perception tensor. We propose to concatenate a scale-invariant Cartesian positional encoding to the perception tensor to allow all cells to access their global position. Then, all cells apply the same update rule, which is parameterized by a 2-layer MLP, and perform stochastic update to finish one step of evolution. The whole process can be expressed by the finite difference approximation of the defined partial differential equation. With the model in hand, we propose to add supervision signals to train our model to synthesize desired dynamic textures. The first supervision is on motion, visualized by optic flow images. We propose 2 ways of defining the target motion. The first one is direct. That is, a handcrafted vector field representing motion direction and strength at each position. The second one assumes that the target motions come from videos. For example, the 3 videos shown here and the accompanied visualization of the optic flow. Accordingly, we design different loss schemes for different target modalities of motion. First, we assume that t steps equals 1 frame of motion. For vector field motion, we match the strength and direction of the generated motion and the target ones, and prioritize the direction matching part. For video motion, we seek a style matching between the generated motion and target one. Apart from matching the motion, we also need to make our model generate desired appearance. For both motion targets, we use only a single image for the appearance target. Again, we use the style matching loss as the objective. We train our model to match the given appearance and motion targets. Here are our results.
We compare our synthesized videos with the current state-of-the-art methods on texture quality and realism. You can see that visually our method achieves smoother results. Since there is no objective metric for evaluating the realism of the videos, we conduct a user study to demonstrate. We have 150 participants and 59 videos from each method. We ask the participants to choose the video that looks more realistic. The columns show the percentage that the method is chosen. As shown in the table, our method is favored among all the other methods. Moreover, we compare the model properties between different methods. As you can see, our method is capable of much faster synthesis and has much fewer parameters than the others, facilitating real-world applications. Moreover, to show the necessity of our proposed modifications to the vanilla NCAA, we conduct ablation studies on them. The first one is on multiscale perception, and as you can see, without multiscale perception, NCAA can generate wrong-shaped or wrong-colored texture videos when using large seed sizes. Our second ablation study shows that Cartesian positional encoding helps our model to synthesize the correct converging motion, regardless of the seed size. But without CPE, the cells don't know their new position and fail to generate the desired motion. Our model has certain limitations. When training with video supervision, we find that our model is sensitive to the motion loss weight, and this can lead to low-quality results. Moreover, it is hard to train our model on videos that change very fast, and some of the synthesized videos look repetitive. For example, the fire video shown on this slide. Here are the references, and thank you for listening.